We will be looking at second order linear differential equations in this video. Now, how do you solve an expression that looks like this? Y prime prime minus 7y prime plus 12y equals 0. Now, y prime prime here is the second derivative of y, and y prime here is the first derivative of y. Now, this is a second order linear differential equation. In order to solve any equation, the first thing to do is to know what type of equation you are working on. Now, for a second order linear differential equation, the general form is P of x y prime prime plus Q of x y prime plus R of x y equals G of x. And when we compare this expression with the general form of a second order linear differential equation, it is easy to identify P of x, Q of x, and R of x as coefficients of y prime prime, y prime, and y here. So because of that conformity, it is easy to identify an equation or expression like this as a second order differential equation. All right. Now, if the expression equals 0, that means g of x equals 0, then it means that the second order linear differential equation is homogeneous. And if otherwise it isn't equal to 0, that is g of x does not equal 0, or the expression equals something else here other than 0, then the second order linear differential equation will be a non-homogeneous one. Now, as P of x, Q of x, and R of x are constants, we can simplify this general form to something like this. And because it equals to 0 here, then we are talking about an homogeneous second order linear differential equation. So let's then go ahead and just consider some basic general hints of solving second order linear differential equation. So now simplifying this general form to this means that we have substituted A, B, and C for P of x, Q of x, and R of x respectively. All right, now in order to solve the like of second order linear differential equations, the first thing to do is to write down this expression for y. Now, the general solution for homogeneous equations is of the form of y equals exponential raised to power rx. So now we write this expression for y. And if y equals exponential raised to power rx, then y prime, that's the first derivative of y, will equal r exponential raised to power rx. And the second derivative of y will equal r raised to power 2 exponential raised to power rx. Now the second step now is to substitute this expression and this expression for y prime and y prime prime respectively in this equation, the simplified form of the general form of a second order linear differential equation. So now when we do that correctly, substituting for y, this for y prime, and this for y prime prime, in this we have this expression. And because the equation is homogeneous, it equals 0. Now we can now divide both sides of the expression by exponential raised to power rx. So we'll be left with this expression, which is a quadratic equation in terms of r. Now, because it is a quadratic equation, we can solve for r using the quadratic formula. Now, there are three case scenarios that may result from the solution to r, or solving for r. And that is when the discriminant b squared minus 4ac is either greater than 0, equal to 0, or less than 0. So each of these case scenarios must be treated uniquely, and they do have their general solutions, unique general solutions. So let's look at these case scenarios one after the other. For the first case scenario, when the discriminant of the resulting quadratic equation is greater than 0, it then means that b squared minus 4ac is greater than 0. So that shows that when solving for r, two distinct real roots will result, r1 and r2. So r will have two solutions, r1 and r2. So in that case, the general solution to the second order linear differential equation will take the form y of x equals c1 exponential raised to power r1x plus c2 exponential r2x, where c1 and c2 are constants, r1 and r2 are the two distinct real roots that resulted from the quadratic equation. All right, let's look at the next case scenario. Now, if the discriminant equals 0, then there is only one real root that results. That is r equals minus b all over 2a. So in that case, the general solution to the second order linear differential equation takes this form. That is y of x equals c1 exponential rx plus c2 x exponential rx. Now r here, because we have just one real root, so we don't have r1 and r2 as we do in the previous case. So r here equals r here, as it is the only real root resulting from the quadratic equation when the discriminant of the quadratic equation equals 0. So from here we can, of course, factorize exponential raised to power rx out, and we can open a bracket and have c1 plus c2x before closing the bracket. All right then. Now, the third case scenario is when the discriminant is less than 0. Now, in such a case, the roots are complex and conjugates. That is, r1 will equal alpha plus beta I, and r2 will equal alpha minus beta I. Now, in that case, the general solution is expressed as y of x equals exponential alpha x, then open brackets, c1 cosine of b of x plus c2 sine of b of x. We'll close the bracket. Now, in this case, the exponential term here represents the real parts. whereas the trigonometric path and cosine functions represent the imaginary parts. All right, I think we can then go straight into solving problems. All right, let's look at this example. Solve y prime prime minus 7y prime plus 10y equals 0. Now, this is a second order homogeneous linear differential equation. Now, the first step to take is to write down the characteristic equation by assuming y equals exponential raised to power rx. Now, by this assumption, the first derivative of y, which is y prime, will equal r times exponential raised to power rx, and the second derivative will equal r raised to power 2 exponential raised to power rx. So now we then substitute these expressions for y prime and y prime prime in this equation. Now substituting as appropriate will result in this expression. So we can factorize this as it is common to each of the elements of the expression. We can factorize exponential raised to power rx, we can factorize it out. And by dividing both sides by exponential raised to power rx, we will be left with this quadratic equation, which is this. So now the next step is to solve the quadratic equation. Now solving this quadratic equation appropriately will give us r minus 5 in brackets and r minus 2 equals 0. So this is a case where the discriminant is greater than 0 and we have two roots from the quadratic equation. So here we have r equals 5 and r equals 2. So the general solution for the second order linear differential equation for when the discriminant is greater than 0 is given by yx equals c1 exponential r1x plus c2 exponential r2x. Now we've been able to determine r1 and r2. So what we just do is to substitute for r1 and r2 in this expression for the general solution. Now we do that by simply writing it down this way. So it becomes c1 equal c1 exponential 5x, as that is one of the roots for r, and c2 exponential 2 exponential raised to power 2x, and that is the final answer. All right, let's look at another example. Solve y prime prime minus 4y prime plus 4y equals 0. Now again, this is a second order homogeneous linear differential equations. You will understand this from our previous explanations. Now the first step to solving this second order homogeneous linear differential equation is to write down the characteristic solution or equation for y, in which we assume that y equals exponential raised to power rx. So we then first find the first derivative and second derivative so we can substitute them into the equation. Now the first derivative is y prime and it's equal r exponential raised to power rx, and the second derivative equals r raised to power 2 exponential raised to power rx. Now we substitute for these we substitute y prime, and y prime prime into the original equation, and we get this expression. So now, as exponential raised to power rx is common to all the elements here, here, and here, I'm talking about the coefficients of r squared, coefficients of r, and this aspect of the equation. So then we can factorize exponential raised to power rx out and divide both sides by exponential raised to power rx. So we'll be left with this quadratic equation. So we can then go ahead and solve the quadratic equation. We can factorize, we can use quadratic formula. So whichever way, we will arrive at this point where r minus 2 squared equals 0. Now, in other words, if we take the root of both sides, we'll just have just a single root solution for r, and that will be r equals 2. So now, for such kind of scenario, when the discriminant equals 0, the discriminant in this case is b squared minus 4ac equals 0. So when the discriminant equals 0 in this kind of scenario, the root looks something like this. We have just a single root, or so to say, a repeated root. And the general solution to such kind of scenario is a case where we have the expression written this way. That is y of x equals c1 exponential raised to power rx plus c2 exponential rx. We can factorize rx out and have it written this way. So when you investigate the discriminant, you will notice that b squared minus 4ac equals 0. And so here we go. This is the general solution, and because we have determined r to be equals to 2, we just simply substitute 2 in this general solution to have the final answer. So we substitute 2 for r in the general solution, and this becomes the final answer. All right, we also want to look at another example. Solve 16y prime prime plus 8y prime plus y equals 0. Now, in order to solve a problem like this, we need to identify the fact that this equation is a second order linear differential equation, and of course it is homogeneous because it is equals to 0. So now the first thing is to write the characteristic equation by assuming that y equals exponential raised to power rx. Then find the first derivative of y and the second derivative, so we can substitute in here. Now this is the first derivative of y, and this is the second derivative of y. Now when we substitute this for y prime prime, and we substitute this for y prime, and this expression for y in the equation, then we get this. So we can factor out exponential raised to power rx, and when we get the next expression, we divide both sides by exponential raised to power rx, and we'll be left with this quadratic equation. Now the next step is to solve the quadratic equation. Now using formula to solve this quadratic equation, of course we know that the coefficient of r squared is a, the coefficient of r is b, and the constant term here is c, and that's we have identified here. So now substituting into the quadratic formula, we can solve for the roots r. Now we have a situation where we have repeated roots minus 1 all over 4. Now this is the repeated roots for r. Now the general solution for such cases where we have repeated roots scenario, the general solution takes this form. And to have the repeated roots scenario is that scenario where the discriminant b squared minus 4ac equals 0. So now when you plug in these values into the expression for the discriminant, you'll discover that b squared minus 4ac equals 0. And that is why we've got this general solution for such kind of scenario. We have explained this earlier, so you should understand why this is so. So the repeated roots, yes, so a repeated roots case scenario. And so next we simply substitute minus 1 all over 4 for r in the general solution, and we simply just plug in minus 1 all over 4 here to have the final answer, and this is what we've done here. All right, so looking at another example, solve y prime prime plus 2y prime plus 5y equals 0. Now in order to solve this problem, we need to first and foremost identify the fact that this is a second order homogeneous linear differential equation. So now the first step is to write the characteristic equation by assuming y equals exponential raised to power rx. So by this assumption, the first derivative of y, which is y prime, equals r exponential raised to power rx, and the second derivative, r prime prime, equals r raised to power 2 exponential rx. Now substituting these values for substituting these values, this for y and this expression for y prime, and this equation for y prime prime, substituting as appropriate in the second order linear differential equation, we have this expression. So then when we factor out exponential raised to power rx, then we have the next equation. So we can then divide both sides by exponential raised to power rx, and we will then be left with this quadratic equation. All right then, so the next step then is to solve the quadratic equation, which is r squared plus 2r plus 5 equals 0. The coefficient of r squared here is 1, the coefficient of r is 2, and this constant, which is c, the coefficient of r squared is a, the coefficient of r is b, and the constant here is c. As identified, then solving using quadratic formula shows that our solution, the roots of the quadratic equation, gives a complex root in this form. So it is either we have minus 1 plus 2 I, or minus 1 minus 2I. So now when we have such complex roots, it shows that our general solution will take the form of the case scenario where the discriminant is less than 0. The discriminant, of course, is b squared minus 4ac. And when we plug in these values, we'll discover that b squared minus 4ac will be less than 0. So that is why we've got complex roots solution for R, really. Now, when we have such case scenario, the general solution to the second order linear differential equation takes this form, and the complex roots can be related to this form of expression, so as to correctly substitute the appropriate values into the general solution. So here, alpha here will be minus 1 and beta will be 2. And that is what we've jotted down here. Now, substituting as appropriate for alpha and beta into the general solution will give the final answer as indicated here. And that is the solution to this second order linear differential equation, which is homogeneous. All right. We can also have a situation where we need to solve an initial value problem. This abbreviation stands for initial value problem, IVP. An initial value problem is a problem that deals with finding the solution to a differential equation given some initial conditions. So let's look at this problem. Solve the initial value problem y prime prime plus 9y equals 0, with y of 0 being equals to 5. In other words, when we substitute in our final solution, we find y of 0, then that should be equated to 5, and y prime of 0 should equal 3. So now let's just solve this problem, and we will then plug in these initial values into the solution and solve as appropriate. So now the solution. Now this is a differential equation, and of course it is homogeneous because it is equal to 0. Now the first step is to assume y equals exponential raised to power rx and find the second derivative. We do not have the first derivative in this question. So, and when we get the second derivative here is equal to r squared exponential raised to power rx. Now we can then substitute this for the second derivative and this for y in the equation. Now when we do that, we get this, and we can factor out exponential raised to power rx and divide both sides by exponential raised to power rx, and we will then be left with this aspect of the expression equals to 0. Now we can solve for r, and that will give us minus r squared minus 9. So this gives us a kind of a complex root where r equals to plus or minus 3i because of the negative sign here. So then the roots of the quadratic equation, or the characteristic equation in this case, are r equals 3i when considering the positive aspect, or minus 3i, which is purely imaginary. Now the general solution to this is, for imaginary roots, we have a general solution for such cases. From this general solution, you will note that the exponential aspect of the equation, where you have exponential raised to power alpha x, isn't there. The reason is because alpha here is, we don't have a value for alpha, and if we assume that to be 0, exponential raised to power 0 is 1. So and when we multiply 1 with this trigonometry aspect of the solution, this remains. So practically, this is the general solution for this problem. So here we just simply substitute 3 for beta in the general solution. So, and doing that gives us y of x equals c1 cos 3x plus c2 sine 3x. Now, from the initial values that we were given, which is the conditions, the initial conditions we were given, y of 0. So in other words, if x is 0, then the whole expression for y when x is equal to 0 will be 5. So so next we just simply plug in the initial value, initial conditions, and solve accordingly. So all right, now let's substitute 0 for x into the general equation. So y of 0 equals c1 cos 0 plus c2 sine 0, and cos 0 is 1, sine 0 is 0. So that gives us c1 times 1 plus c2 times 0. Now 0 times c2 will give us 0, and c1 times 1 will give us c1. So this y of 0 will equal c1. But of course, the initial boundary condition, initial condition, so to say, shows that y of 0 equals 5. So now that means that because y of 0 equals 5, then it means that c1 equals 5. So that is for this first initial condition. Now the second initial condition is y prime of 0 must be equal to 3. Now what we then do is to first compute y prime of the solution we've got. So the y prime, that's the first derivative of the solution, becomes minus 3 c1 sine 3x plus 3 c2 cos 3x. You remember that it was cos 3x we've got here, and the derivative of cos 3x is minus 3 sine 3x. Initially, recall that we've got sine 3x here and c2 sine 3x, and the first derivative of that becomes 3 c2 cos 3x. Now we've computed the first derivative of y, which is this. Now the next initial condition we want to work with shows that when we substitute 0 for x, so y prime will equal -3. So now let's substitute 0 for x and let's see what we've got. So we just then plug in 0 wherever we found x, and let's see what results. So here sine 0, we've got sine 0, and this here we've got cos 0. Now this aspect results in 0 because sine 0 is 0, and this sign results in 1 because cos 0 is 1. So 1 times 3c2 plus 0 times 3 minus 3c1, all of this reduces to 0. So what we then have left is 3c2. So now, but from the initial condition, this guy here equals -3. I mean this guy here. So now instead of this, let's plug in -3 here. So we then have -3 equals 3c2. -3 equals 3c2 here. So we're given this. So then we can then say divide both sides by 3, and c2 will equal -1. So then the final solution, because we now have values for the constant terms, c1 equals 5 and c2 equals -1, then the general solution can now become y of x equals 5, which was initially c1, but we have a value for c1 now, and we also have a value for c2. So instead of c2, we have -1 there. So and our beta was 3. So the solution, the final answer now becomes 5 cos 3x minus sine 3x. Of course, we got this by simply substituting the respective values for c1 and c2, and that is our final answer. All right, now we want to solve boundary value problem as it relates to differential equations. BVP here means boundary value problem. Now the question is, solve the boundary value problem y prime prime minus 4y prime plus 4y equals 0. We have these boundary conditions. These are specific boundary conditions connected to this question. So with y of 0 equals 2 and y of 1 equals 8 exponential raised to power 2. So you can see that the initial conditions we were given were such that you have y of 0 and y prime of 0. But here we have boundary conditions that shows that the value of x in the y expression is 0 at one end, but there is a value for x at the other end, and this is why we call it boundary value problems. So the value of x increased from 0 to a particular value, unlike the initial value problem where what we've got is just some initial conditions. All right then, let's go on to solve this boundary value problem. Now the characteristic equation to solve this second order linear differential equation, which is bounded by this specific boundary conditions. So we then assume y equals exponential raised to power rx. We'll determine the first derivative of this, which is this, and the second derivative of this, and plug in the values into the equation. And so now, substituting appropriately, we get this, and we can factor out exponential raised to power rx. So dividing both sides by exponential raised to power rx will then result into this characteristic equation, which is a quadratic equation. Now we can then factorize the quadratic equation to have r minus 2 raised to power 2 equals 0. So this is a form of a repeated roots kind of case, where we just have a single real root for r. Now, the general solution for such kind of scenario is y of x equals c1 plus c2 x exponential raised to power rx. Now, the next thing we do is substitute for 2 for r in the general solution, so we can get the next expression. So then from here we can then apply the specific boundary conditions and move on from there. So the first boundary condition is to substitute 0 for x in y. And of course, when we substitute 0 for x, 0 multiplied by c2 becomes 0, and c1 remains as it is. Then exponential raised to power rx, r was 2 times 0 becomes 0, and anything raised to power 0 is 1. So what will then be left here is simply c1, because this goes off, this becomes 1, so we have c1. Now the specific boundary condition here says y of 0 equals 2. So it then means that c1 equals 2, because y of 0 equals 2. So when we plug in 2 here, it shows that c1 equals 2. So we then again apply the second specific boundary conditions, which is y of 1 equals 8 exponential raised to power 2. So when we substitute 1 for x in the solution for y, we have c1 plus c2 times 1 and exponential raised to power 2 times 1, and that gives us this expression. Initially, we had determined c1 to be equal to 2, so we can just go ahead to substitute as appropriate, so we can get a value for c2. Recall that the boundary condition we're working on states that y of 1 equals 8 exponential raised to power 2. So basically, all this equals to 8 exponential raised to power 2, as we've got here. So now we divide both sides by exponential raised to power 2, and that goes off. So we are then left with c1 plus c2 equals 8. And from applying the first specific boundary condition, c1 had been determined to be 2. So when we substitute 2 for c1 and plug it into this equation, we can easily determine c2, which gives us 6. So the final solution then becomes y of x equals C1 was here and C2 was here. So having determined the value for C1 and C2, so we just simply substitute for C1 and C2 with the appropriate values. So we have 2 plus 6x close brackets exponential raised to power 2x, and that is the final answer. So far, we have been looking at homogeneous second order linear differential equations. So this time around, we want to look at non-homogeneous second order linear differential equations. So the question is, solve the non-homogeneous differential equation y prime prime plus 4y prime plus 4y equals x raised to power 3. Now, because this second order linear differential equation is not equal to 0, it is equal to what we call g of x, which is x raised to power 3, then it shows that it is non-homogeneous. All right, now there are basic steps to solving non-homogeneous differential equations, and that involves solving the complementary solution or finding the complementary solution separately and the particular solution separately. The complementary solution here has to do with the homogeneous aspect of the differential equation, while the particular solution has to do with the non-homogeneous part of the differential equation. So let's just look at the steps to solving this type of problems. Now, the first step is to find the complementary solution yc of x. So the complementary solution, or the complementary part, as earlier mentioned, is the homogeneous equation y prime prime plus 4y prime plus y plus 4y equals 0. So this is homogeneous because it is equal to 0. So now we first of all solve this, and in solving this we assume y equals exponential raised to power rx. Then we find the first derivative of that, which is this. We find the second derivative of that, which is r raised to power 2 exponential raised to power rx. So then we find the characteristic equation by substituting for y and y prime as well as y prime prime in the homogeneous differential equation. And when we do that, we get this expression. So when we divide both sides by exponential raised to power x, we have this quadratic equation. So factorizing this quadratic equation, we have r plus 2 in bracket raised to power 2 equals 0. Now, for this type of solution, which gives us just one real value for the roots, we call it a kind of a repeated roots kind of scenario. So for this type of scenario, the general solution, as we've treated in the previous as we've treated previously in this series, shows that the general solution to such kind of scenario is such that y of x will equal c1 plus c2x, all in brackets, then exponential raised to power exponential raised to power rx. And of course, with our r is -2, so substituting -2 for r gives us what we've got here. Now, of course, this is the complementary solution as it relates to solving non-homogeneous differential equation. Now we then move on to the second step, which is to find a particular solution. Now, the particular solution aspect deals with the non-homogeneous part of the problem. Now, in order to do that, we look at what we've got here. Basically is a polynomial. We consider this a polynomial of the third degree. And for this reason, we assume that the solution, the particular solution, equals ax raised to power 3 plus bx raised to power 2 plus cx plus d. And because it is a polynomial of the third degree, definitely that polynomial of the highest degree, which is x raised to power 3, will have a coefficient. It is assumed it will have a coefficient which is yet unknown. Then it goes on and on with decreasing power of the polynomial until you have the power of the polynomial decreasing to 0. So the responsibility will now be to determine what the values of all these constants will be. Now let's assume we have a polynomial of, say, degree of the second degree, like x raised to power 2. Then you don't need this. You will assume for the particular solution will be ax squared. Let's say if this is x squared or 5x squared, then we have ax squared plus bx plus c. So it depends on the order of the polynomial you've got here, or what the expression for the non-homogeneous part, that is g of x, is. That will inform what you will assume to be your particular solution here. Now, so as we have rightly assumed this to be the particular solution, then we have to compute the first and second derivative of this assumed solution. Now, the first derivative of this will be 3ax raised to power 2, 2bx plus c. The derivative of x constant is 0, so that goes off. All right, then the second derivative will be 2 multiplied by 3, that will be 6ax plus 2b. So next we substitute for the yp of x, y prime p of x, and y prime prime p of x into the differential equation, and this is the differential equation. So y prime prime p of x, which is this, we substitute this for this, and this of course is 6ax plus 2b. So that has been substituted as appropriate. Then we have 4y prime. Y prime is 3ax raised to power 2 plus 2bx plus c, so multiplied by 4, which is the coefficients of y prime here. Then we have 4 multiplied by y, and y is ax raised to power 3 plus bx raised to power 2 plus cx plus d, all equal to x raised to power 3. So now we simply walk around these various expressions, remove the brackets as appropriate, collect like terms, and we then begin to relate the coefficients in order to determine A, B, C, and D. So now we expand the terms. expanding this will give us 12ax raised to the power 2, and that's what we've got here. 4 times 2 gives us 8bx plus 4c. Then expanding this gives us 4ax raised to the power 3 plus 4bx raised to the power 2 plus 4cx plus 4d equals x raised to the power 3. Now we then collect like terms. The like terms as it relates to x raised to the power 3 is just 4ax raised to the power 3. Then plus we've got coefficients of x raised to the power 2 here. We've got two like terms. That is 12a and 4b. So we've got that combined here, grouped. Then the coefficients of x, we have 6a, what other one, 8b, and 4c. So we also group that as the like term, which is a coefficient of x. So finally, we write down the constant terms, 2b plus 4c plus 4d equals all equal x raised to the power 3. Now what we then do is to equate coefficients of like powers of x. Now for the first one, coefficients of x raised to the power 3, which is this. So when we relate the coefficients of the like powers, that will give us 4a equals, the coefficients of x raised to the power 3 here is 1. So that will be 4a equals to 1. Now, making a the subject of the formula, we simply divide both sides by 4, and that will be a equals 1 over 4. So a have been determined. So now the coefficients of x squared. In this case, the coefficient of x squared here is 12a plus 4b, and the coefficient of x squared here is 0. So we then say 12a plus 4b equals 0. Then already we have determined the value of a, which is 1 over 4. So we substitute 1 over 4 for a in this equation to find b. Now, if done appropriately, b will equal minus 3 over 4. We are moving on. Then for the coefficients of x, which is this, we have 6a plus 8b plus c, and the coefficient of x on this other side is 0. Of course, we don't have coefficient of x here, so that is 0. So then the expression becomes this, and we substitute 1 over 4 for a, we substitute minus 3 over 4 for b, and work out solving for c. Now, if done appropriately, c will equal 9 all over 8. So we've determined a, b, and c. So let's move on to d, the constant term. We've got no constant term for the right hand side. So for the left hand side, we have 2b plus 4c plus 4d. So that will equal 0. So from this expression, we have a value for b, we have a value for c. So we just simply plug in those values in substitution for b and c, and we can solve for d. Now, if done correctly, d will equal minus 3 all over 4. All right, so let's move on to the next steps. Now, having determined the values of a, b, c, and d, we can then proceed to expressing the particular solution, yp of x. So the particular solution will equal 1 all over 4 x raised to the power 3 minus 3 all over 4 x raised to the power 2 plus 9 all over 8 x minus 3 all over 4. So the final step of the solution is to combine the complementary and particular solution. So the general solution then, so the non-homogeneous differential equation is the sum of the homogeneous and particular solution. The homogeneous solution, of course, is the complementary solution. That is y of x equals the complementary solution yc of x plus the particular solution, that is yp of x. So the complementary solution is this, and the particular solution is this. So just simply adding them together gives us the final answer.